Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Thanks very much for joining us today from wherever in the world you might be listening. We really appreciate you taking the time out. Our last podcast talked about thermal management in the EV battery pack and the importance of cooling, particularly with high rate charging. As charge rates are going up and up, because we all want faster recharge times for the electric vehicle, it's a real sort of key benchmark. Then there's some issues in terms of thermal management inside the battery pack and keeping the cells cool. So that was really topical because it was very hot outside and there's been some issues. So today it's still very hot outside. So we're going to talk about thermal management again. But this time we're not going to look at the battery specifically. We're going to talk about all of the other components on the vehicle, the inverter, the motors and everything else. So at Avid, we've got two different terms that we use. We talk about outside the box and inside the box thermal management. So the outside the box stuff, it's the fluid transfer system, the pipe work, the pumps, valves, fans, heat exchangers, and all of those components. And the outside-the-box cooling system, it's going to be the largest parasitic power consumer on the vehicle. So the energy required to keep the driveline components and the occupants of the vehicle at the right temperature is really significant. And that energy eats directly into battery capacity for actual driving. So it's well known when it's hot outside, an EV doesn't give you as good range as when it's not so hot. And that can be quite significant, maybe 20-30%. So you can see the potential for improving vehicle range in improving the efficiency and optimization of that thermal management system. At Avid, we're pretty well known for this. So in terms of high performance components like electric coolant pumps and electric cooling fans, we've got a lot of systems level knowledge and component level knowledge, and we can really help to design a highly optimized thermal management system for an electric and hybrid vehicle. So then on the inside the box, what we're talking about there is the internal heat exchange, heat sink design inside the component and the thermal characteristics of the component itself, so how it is generating heat. And the design requirements of the inside the box cooling system are really, really important because they drive the requirements elsewhere. And really, you can see if you get it wrong here, a bad design can lead to much more cost and power consumption elsewhere. And it can be something quite simple, like for instance, you design the heat exchanger in the inverter to have a very high pressure drop. And that seems like a good idea at the time, but then the pressure drop requires you to have a very power-hungry pump on the system. One of the key issues with electric vehicle, particularly with high performance, is thermal management inside the component. So electric motors and power electronics, really, as we push for higher and higher power densities out of these things, which is important because we want to reduce the weight of the drivetrain, and the weight also directly feeds back to the range again. You know, a heavy electric vehicle will require more energy to get from A to B than a light electric vehicle. So there's a real value in terms of taking weight out of the drivetrain components. So as we're working to try and increase the power density of all the devices in the EV, the main thing that we're really working against is the thermal management of that device. So trying to deal with the heat that is generated in the device in its operation. So even if you imagine something like a 200 kilowatt inverter, that's going to be really efficient. So maybe 95% or more efficient. Which is fantastic. So compared to a combustion engine, that's loads better. Combustion engine, 50% efficient, you can have 200 kilowatts of heat to deal with. But in an EV, you've only got 10 kilowatts of heat. So it's hardly any heat to deal with, but it's going to be in a really, really tiny area. So the switching devices are very small, and that heat will be generated across a few square millimeters. So that can cause some significant challenges inside the device, like literally the heat sink material can be easily just vaporized if you don't get the thermal management right. And that's why things like inverters tend to have minimum coolant flow requirements that are greater than the theoretical coolant flow required for the sort of low power output levels. So there's an awful lot in that, and getting it wrong can have some pretty bad consequences. There's three main strategies for dealing with and improving thermal management in in these devices in the electric vehicle powertrain. And, it's not rocket science. It's pretty obvious, really. So the first one is reducing the source of the heat. So reducing the amount of heat you're generating by improving the device efficiency. The second one is improving its ability to reject heat through good thermal management. And the third one is improving the resilience to heat by using improved materials. So first of all, improving efficiency. Well, to explain this, really, we have to understand what's happening. To make a brushless motor spin, we need power electronics. So the power electronics are used to switch the phases of the motor on and off in sequence. That creates a reaction between the magnetic field in the motor stator and the magnetic field in the rotor, and that's what makes the motor rotate. In order to give us speed and torque control for the motor, we need to have the switching taking place at quite high frequencies. So each phase of the motor has to be switched on and off multiple times for each revolution of the motor. Now, in power electronics, it's not like a light switch where you go from on to off and the transaction is immediate. As you turn the devices on that are used in a typical power electronics device, they have a transition. They go from low impedance, which is equivalent to the switch being closed, to high impedance, which is equivalent of the switch being open. And as that transition happens, the resistance, the impedance of the device ramps. And in this period of time when it's ramping, the device is conducting significant amounts of current, but it has an internal resistance. And that's where you get heat generated in the device. So the heat is proportional to the square of the current times the resistance. So if we can reduce the resistance of the device, we can significantly reduce the heat being generated. If we can reduce the current in being switched by some means, we can also significantly reduce the heat being generated and improve the efficiency. So it's a really important to think about. But how can we do it? What can we do to reduce that heat generation? Well, basically, the quest is out to find devices that have got better switch-on characteristics. So there's lots of complicated terms involved there, but essentially what we're looking for are things that switch on very quickly and don't go through that ramp of resistance as they turn on. So basically getting rid of the turn-on resistance. These are typically called wide bandgap devices, so silicon carbide and gallium nitride. Now, something that came out fairly recently surprised me. So the Tesla Model 3 is actually using silicon carbide MOSFETs in its inverters. Now, you might say, why is that a surprise? Well, so silicon carbide MOSFETs are currently not widely used because they're quite expensive compared to a conventional IGBT device. And the Model 3, as everyone knows, is meant to be a very affordable car. So you would not expect it to necessarily have very high-tech, expensive switching devices in its inverters, but it does. And I think really what that tells you is an awful lot about the system-level optimization that you can carry out. So Tesla have clearly made a conscious decision to invest in higher-end switching devices in the inverter. But I think the trade-off and how they paid for that was through the ability to simplify the rest of the system, so remove components from the thermal management system. So they haven't deleted it completely, but if you compare the thermal management system in the Model 3 to the Model S, significantly reduced in terms of complexity. There's fewer valves. There's a nice integrated valve module. There's fewer pumps in there as well. So it's really a simpler thermal management system. The other thing that they'll be able to do is switch higher frequency. So they can use higher RPM motor on the vehicle, which means they can have a smaller, lighter motor, and various other things. So I think they've put a lot of thought into that in terms of investing more in silicon carbide MOSFET compared to conventional IGBT. And silicon carbide is good stuff. It's got less than half of the switching losses of a comparable IGBT and can be run much higher frequencies. The other thing about silicon carbide, which we get onto later, is it's also much more tolerant to high temperatures. So we'll come back to that. So the second thing I mentioned earlier in the introduction to this section was we can do things that are designed to improve the heat rejection. So what do we mean by that? Well, we can improve the ability to get heat out of the devices. So things like looking at higher specification circuit board material, it's got improved thermal properties, encapsulants for electronics and motors that have got good thermal conductivity, which can help to get heat away from the devices in an improved manner. Improved heatsink design, improved methods of getting heat out of the device. So there's a couple of really interesting examples of that. So one is in the BMWs where they've got the direct refrigerant system. So that is a very clever system. So instead of using water glycol to cool in some elements of the EV driveline, they're actually using direct evaporation of refrigerant. So that gives them basically two-phase cooling. So they can get much, much more effective heat exchange going on by using direct evaporation inside there. The other example that I've seen recently is the transition from the battery pack thermal management in Model S, the original Tesla Model S cars, to the new battery thermal management system in the Model 3. So in the old cars in the Model S, the cooling was by means of a serpentine pipe that went through the battery pack, but it didn't make contact with every single cell in the battery pack. It kind of went by big groups of cells, and it sort of took heat out of the vicinity, but didn't make contact with every single cell. The battery pack in the Model 3 is quite different. It's essentially got much, much longer cooling tube running through it, again in a serpentine fashion. But pretty much every single cell is attached to the cooling tube. So the cooling tube goes past, and it's got cells on either side of it. So that basically the heat transfer contact area inside that battery pack is massive compared to the Model S and the Model X battery packs. Much, much more contact area with the cells to the cooling pathway. So there's lots of things that you can do with the design of the devices themselves to improve heat rejection in the device. The third thing I mentioned was improving the resilience to heat. Okay, so this is quite a big area, and as a general rule, I have a little saying. I always say electrons don't like getting hot. So normally it is a good idea to keep them cool. However, sometimes it might not always be possible, and it might be better to sacrifice a little bit of efficiency and run the components at a slightly higher temperature if that allows you to basically optimize the thermal management system, reduce coolant flow rates, increase the temperature gradient from the coolant. So even increasing the coolant temperature by 20 degrees to ambient can have a huge impact in terms of the heat rejection effectiveness you can achieve with the system. So improving the resilience of the devices themselves is really important. And there's a few key devices that are very tolerant. And there's two ways really in which, or two things you've got to really look at. So the switching devices themselves, the traditional IGBTs, they start to break down if they get too hot. So you've got to be really careful to keep the IGBTs at the right temperature. The nice thing with the new wide bandgap devices is silicon carbide, maybe like 50 or 60 degrees higher operating temperature is possible with those compared to a traditional IGBT. So you can run silicon carbide much, much hotter than you can with a conventional IGBT. But there are other devices in a system, so things like capacitors, which can get hot. The value, the properties of the capacitors can change over the operating temperature range. You also got the other things like microprocessors, which break down and can only work through certain temperature range. So there's lots of things to take into consideration. If you're going to think about increasing the operating temperature, I think you basically have to get quite clever in terms of how you segregate and thermally manage inside the device. So you might be able to run your silicon carbide MOSFETs hotter than you could run your IGBTs, but it's unlikely that you're going to want your microprocessor getting too hot. And you're going to have to be very careful with capacitors. And there's a lot of really interesting things happening, particularly higher temperature capable capacitors and things going on there. In the other devices on the system, so basically electric motors, there are a couple of key areas where it's possible to improve thermal resilience. So in a motor, electric motors, the main problem with thermal resilience is in the windings. So basically, the windings, it's copper wire, which is covered in a very, very thin insulation material. And that insulation material breaks down as it gets hot. So if you get the motor windings too hot, basically you shorten the life of the motor, and eventually it'll give up completely and leads to failure. So we're very careful with how we manage the temperature in the motor windings to make sure they don't get too hot. And there's an element there of preventing premature failure and making sure we get the right design life, but then also preventing a catastrophic instantaneous failure if we have a hotspot building up inside. So there's lots of things going on at the moment with really interesting new insulation materials that have got better thermal properties than the current insulation materials, so higher operating temperatures and better things you can do there. Also, lots of people looking at doing things with basically highly thermally conductive, but electrically insulating potting materials, so we can get heat out of the windings and into the cooling jacket of the machine much more quickly. The other thing we've got to be very careful of in a permanent magnet motor is the rotor magnets. So they can basically, the rotor magnets will demagnetize if they get too hot. And that's a design limit in the machine. And getting heat out of a rotating motor rotor isn't simple. So we can't have like a cooling jacket running through it because it's spinning, and that would need seals. We can spray with oil, but oil spray cooling's got its limitations. It's got very low heat transfer potential. And also oil spray cooling introduces extra parasitic losses into the system compared to a conventional water glycol. It takes a lot more energy to pump oil around a system than it does to pump water glycol because oil is more viscous. You need extra heat exchangers, you need oil pumps and things like that. So oil cooling does have a role to play in some circumstances, but it does add extra complexity from the system. So removing heat from an electrical machine is always complex because it's always deliberately packed full of copper and rotor magnets. Making space inside it for active cooling really does impact on the performance and the packaging density. So some designs of electric motor might seem very good on paper, but then they're really compromised in their real world performance because basically they've got very poor internal heat rejection capability. So what this means is if you can't get rid of the heat being generated, the device will overheat. So you might have a really impressive headline peak power figure, but basically you can only achieve it once, and then you won't be able to get back to it again until the device has taken a long time to cool down, rather than being able to repeatedly expose it to that very high performance figure. So the other thing you do have to be very careful of is thermal stress as well. So that's not exposing devices to sudden swings in temperature, because that can cause issues with differential thermal expansion in the materials. So thermal shock is something really to take into account in the design of the components themselves, but then also in the control of the thermal management system. You don't want to be thermally shocking your electronics or your electrical machine if you can at all help it. So that's it for today. That's the key areas: thermal management inside an EV. Why is it important? We're going to be keeping a really close eye on developments in this area. Obviously, there's things coming out of Avid all the time in terms of new technologies, improving the efficiency of the performance of pumps and fans and new heat exchange technologies and things like that. We'll keep you abreast of those developments through these and future podcasts. Thanks very much for taking the time out to listen to us. Don't forget to subscribe to our channel, hit like. If you've got any questions on what's come up today, I appreciate we're trying to cover quite a big topic in a very short podcast. If you have questions, please feel free to leave them below. Send us an email. We've had some really good feedback already to some of the other earlier podcasts that we've done, so really appreciate that feedback. Keep it coming in. So feel free to ask us some questions. That's all for today. Thanks very much for joining us.